everyone, welcome back to NEET World. So today we will be discussing optical isomerism. So when it comes to optical isomerism, we need to understand this optical activity. So do you have any idea on optical activity means? What do we mean by optical activity? I have given little introduction about this optical activity in the last class. For example, I am taking a light source from here. Okay, so this is a normal white light, you can say. I am placing a nickel prism here. What I am doing, I have taken white light, normal light, I passed it through nickel prism. So now this white light will get polarized like this. Now I can call this light as plane polarized light. We'll get single beam of light, I can say single plane polarized light we have here. Okay, so now when I am taking this plane polarized light and passing through the solution which is present in this cuvette tube. Okay, what we have here? Solution, that is if I am saying this is optical active solution, I have a solution in this tube now. See, through this tube I am passing this plane polarized light. Now what happens is, this whatever the light ray you are seeing like this will get deflected, or it will be turns either clockwise or anti-clockwise. Okay, so this rotation of plane polarized light either right side or left side will be possible by optical active compounds. What I am saying? Only those compounds will rotate this plane polarized light which are optically active. Okay, if a compound is rotating this plane polarized light clockwise direction, we can consider it as dextro-rotatory. What is that? Dextro-rotatory. I can write dextro, it means indicated with small d or plus. And one more, if it is rotating anti-clockwise direction, we can call it as levo-rotatory, indicated with small l or minus. Okay, so these are the two things you can understand here. One is dextro-rotatory and levo-rotatory. Sir, if a solution is not rotating plane polarized light means that is not optically active. If it is optically active, then only either the plane polarized light will be rotated either clockwise or anti-clockwise. If it is clockwise, we can call dextro, and anti-clockwise will be levo. Is this clear or not? Right. Next here, for example, how can we identify optical active compounds? By looking at the compound itself, like theoretical way. Yes, we have some ways to do that. So first one is, compound should contain chirality. Chirality means what? Like handedness I am saying. In simple words I am saying it as handedness. It means if you observe your right hand and left hand, how do they differ? I mean, your right hand looks like mirror image of left right now. So if you place this right hand on your left hand, I mean if this is real image, I am placing a mirror here and it's mirror. There is a mirror, it will be the mirror image of this hand right now. So now you take your right hand and keep on its mirror image.
No, it is not superimposing.
Are they superimposing? No. See, our thumb fingers are at different position, and here little finger, index finger is there. So this is not superimposing. If they are exactly in this kind of scenario, then we can say superimposing. But if I place it like this, they are not superimposing. So those kind of compounds which are not superimposable and mirror images are called enantiomers. What I am saying? Enantiomers. Now before that, how can we identify this chirality looking at the molecule? For example, first way is to identify chiral carbon. Chiral center I can say. Okay, so chiral center means, or chiral center or chiral carbon I am saying. What is the valency of carbon? 4. It means carbon with sp3 hybridization should be present now, should contain 4 all 4 different groups, then that will be considered as chiral carbon. For example, carbon like A, B, C, D. See, A, B, C, D means 4 different groups now. Now this carbon is considered as chiral carbon. Now it will be optically active. With compounds with 1 chiral center are optically active. What I am saying, compounds with 1 chiral center will be optically active. Now sir, what if compounds are having more than 1 chiral centers? Yes, those are also optically active, but not all the cases. See, there are few compounds having more than 1 chiral centers. Okay, see what we know, if chiral center is present, optically active. There are some cases like compounds containing chiral centers, but they are optically inactive because of some other factors. I will show you that. Okay, so what are those factors first? If the compound contains plane of symmetry, I am writing plane of symmetry or center of symmetry, then those are optically inactive. What I am saying, optically inactive. See, even the compound contains chirality, chiral center. If they has plane of symmetry or center of symmetry, molecule become optically inactive. Now let us see some example for understanding purpose. Tell me, do we have any chiral center in the first molecule? Identify, do we have any chiral center in the first molecule? Yes or no? Yes. Where it is? Here. This carbon is having 4 different groups, so it is chiral. Try to highlight it with star mark. Now what about this molecule? Yes, here we have 1 chiral center and here also. Okay, next, what about this? Is this a chiral carbon? See, this is a methyl group, this is also a methyl group. It means this is optically inactive. Okay, it's not a chiral carbon. Next, what about this compound? This one. Yes or no? No. Why no? Because this carbon is not a chiral. This is also not a chiral because both methyl groups only. Next, one last question here, tell me. Do we have any chiral centers?
No.
Look at here. And what about this?
Sir, but is a ring?
Even it is ring also, no issues. If it is has a carbon with sp3 having 4 different groups, consider it as chiral carbon. Now I am telling you one more thing here. See, I have a molecule like CH3, OH, OH. For understanding purpose I am writing OH, H, CH like this. Now tell me, here this is a carbon, this is also a carbon. Is this carbon is having 4 different groups or not?
Yes.
Like bottom one group, above methyl group, OH, H, 4 different groups, so chiral center. This one also chiral center. Now it has 2 chiral centers. You might be thinking it is optically active, but it is optically inactive. Why it is optically inactive? See, what is one more factor I told you here? Condition. If the molecule contains, even though if it contains chiral centers, along with that if it is having plane of symmetry or center of symmetry, optically inactive. So now look at this molecule. Plane of symmetry means I can pass a plane like this. See, I am passing a plane like this, so that the plane is dividing this molecule into 2 equal halves. Then we can consider it as plane of symmetry is present in the given molecule. See, this is the plane of symmetry we have right now. So if a molecule is divided into 2 equal halves, we can consider it as plane of symmetry. Okay, if plane of symmetry is present, we can say it is OP, optically inactive.
Sir, what if OH place there is a CO.
You tell me, I will write here.
C,
CH3.
now same, but in OH position there is one more functional group other than.
Like chlorine is fine. Now it is optically active.
No plane of symmetry.
Yeah. Look here, HH is fine, same. But this side OHCl, are they same? It means no plane of symmetry. So no POS, plane of symmetry. It means optically active because chiral center is present here and here. So it is optically active. Is this clear? Right. Next, one more thing. I have a cyclic compound here. I am writing same cyclic compound. Now identify number of chiral centers. We have here one chiral center and here, right now. But if I pass a plane like this, what happens? It is dividing into two equal halves. Then that plane of symmetry containing compounds are optically inactive. Is this clear or not? Right. Next. Here I have told you that if it is optically active, when I pass plane of when I pass plane polarized light through that solution, rotate either right side or so if one molecule, one isomer rotates right side, other will rotate left side. So it means at each chiral center there are two possibilities. It can be a dextro or it can be a levorotatory. It can be a dextrorotatory or a levorotatory. So how many chiral centers are there here? Two. One chiral center is there. So it can be a D form or it can be a L form, like this. Okay. So each molecule can be a D form or a L form. So now I will tell you one more thing. How many chiral centers are there? In this second molecule, two are there. So at each chiral center we have two things. There is a configuration called, there is a rule of configuration. That is what absolute configuration. At each chiral center it can be have R configuration or it can be a S configuration. Now what I am saying, R and S configuration. This configuration, for example, R configuration is having dextrorotatory property. S will be having now levorotatory. If R is rotating like right side, S will rotate like that. Okay. So now how many chiral centers are there here? One and here one. It can be R, here also it can be R. So it means it can be RR kind of product, or it can be RS, or it can be SR, or it can be SS. So number of chiral centers are 2. Therefore, how many isomers we are getting? 4. So you can simply use 2 power n. At each chiral center there are two possibilities. Just count number of chiral centers possible in a given. So here 2 are there now, so 2 power 2. What is your answer? 4. So similarly you tell me for this molecule, how many chiral centers are there? 2. It means 2 power 1. How many chiral centers? Here one chiral center. This is not a chiral center now. Methyl means. So only one chiral center is there. 2 power 1 means 2. One is R, another one is S. Okay. Now tell me for this. 4. What are those? Like 2 power 2. 4. Both can be RR, both can be SS, or one R, S, or S, R. Is this clear? Now one more thing, sir. Now how many optical isomers are possible in this case, sir? See, it can be, both can be RR.
Sir, but it is optical.
I will tell you. Both can be RR, or one can be RS, or it can be SR, SS. Right now. So now I am trying to arrange this molecule in different formats. Look at here. CH3, OH, H, H, OH, CH3. Same molecular formula only now. But does this molecule has plane of symmetry? No. Now this can be optically active. It means for a particular molecule, by just changing this spatial rotation of atoms, spatial orientation of atoms, we will get different isomers. Those are called stereoisomers. Out of that, some might be optically active, some might be optically inactive. If it contains plane of symmetry, optically inactive. Plane of symmetry, center of symmetry present, then optically inactive, even though it has chiral center. Okay, now it has chiral center but plane of symmetry is there, optically inactive we are saying. Okay, so now here we have chiral centers but no plane of symmetry, this will be optically active. So you can remember one thing, in these compounds, for example, see this is a plane of symmetry now. For example, here it is having R configuration, here it will be have S configuration. If above one is S, below one will be R. When there is plane of symmetry in the molecule. Okay, are you getting what I am saying? If above chiral center is R, then below chiral center will be S. When if it contains plane of symmetry. If above one is S, below one will be R. Therefore, if R configuration is rotating right side, S configuration rotates left side. I mean like this.
Okay.
I mean, what about net rotation? One is clockwise, another one is anti-clockwise. So net rotation becomes 0. So will that plane polarized right will rotate anywhere? No, because net rotation is becoming 0. Therefore, the compounds which are having different configuration at different like this, which is having plane of symmetry, are optically inactive because their net rotation is 0. So RR is optically active, SS is optically active. But here RS or SR both are same only now. See, for example, I am saying above one is R, below one is S. Just keep it like this.
Above one is S, below one is R.
Both are same only now. It means these molecules are now same. Okay, so in this case, how many are possible? Just 3. 1, 2, 3. 3 isomers are possible. Okay, and now this RS or SR is there now. These are both of them are same, I am saying. Now, what is the name of this kind of molecules? If there is plane of symmetry like this, you should call them as meso compounds. What I am saying? Meso compounds. So meso compounds are optically active or inactive?
Inactive.
OP inactive. Why they are optically inactive? Because of
Plane.
because of plane of symmetry, you can say, or in more proper term you can use here is due to internal compensation. What is this internal compensation? See, one is rotating right like clockwise, another one is anti-clockwise. So they are compensating each other now. Therefore, I can say internal compensation. What exactly internal compensation means? Within the molecule, one is R, one is S, one is clockwise, another one is anti-clockwise. Therefore, within the molecule only happening now, therefore net rotation becoming 0. So that is seen in which compounds? Meso compounds.
Can you define meso compounds?
Meso compounds are optically inactive because presence of optically inactive or presence of plane of symmetry. Or specifically, if I want to mention, meso compounds are optically inactive due to internal compensation. Internal compensation. Kalyan, good evening. You just go back and you can rewatch it. What is optical activity? I have clearly explained. So try to come early from next time onwards at least. Okay, next. Is this clear? Now what I told you, if one chiral carbon is there, see this plane of symmetry scenario will be seen. When we will be seeing? See if there is minimum of 2 chiral centers. If only one chiral center is there, do we have plane of symmetry? No. Chiral compounds with one chiral centers are always optically active. You can write this statement in your books. Compounds with one chiral centers are always optically active. In case of compounds with multiple chiral centers, there should not be any plane of symmetry or center of symmetry, then only they will be optically active.
but their isomers can be active.
Multiple chiral centers. If a compound has multiple chiral centers with no plane of symmetry, or center of symmetry, COS you can write, POS and COS, plane of symmetry or center of symmetry, with no plane of symmetry or center of symmetry, then they are optically active. What is the note point you can make from here?
All compounds of the center are always.
Chiral carbon is not the ultimate criterion of optical activity. That must not contain any plane of symmetry or center of symmetry. Then only it will be optically active. Okay. Next. Now I am taking here few molecules. See, CH3, OH, H, OH, CH3. Now tell me what is its mirror image? CH3,
OH left side.
See this side OH, here H, here H, CH3. Okay, for understanding purpose, if you want, you can take methyl or ethyl, some other groups like C2H5, C2H5. Is this a mirror images or not? This is a mirror, I can say. Now bring this molecule and keep it on it. Are they superimposing? Are they merging? No. See, CH3 ethyl can be happen, but this OH will goes on to this hydrogen. It means it's not superimposing. So these 1 and 2 are called enantiomers. What I am saying? A new term? Enantiomers. So now what is mean by enantiomers? How can you define this enantiomer term? Enantiomers are those stereoisomers which are non-superimposable mirror images. See, these two are stereoisomers or not? How do they differ? They differ in the spatial arrangement of atoms only, like OH right side, OH left side, like that only. Okay, after that, stereoisomers, what I am saying, they are not superimposable mirror images. See, 1 and 2 are mirror images or not? Yes, mirror images. Are they superimposing? No. Then we can call them as enantiomers. Is this clear or not? Now our left hand and right hand become an example of enantiomers only. Okay. And hand gloves also? Okay, enantiomers only. Next. Yeah. Now, what I am doing here, you can observe. Okay, here I have written one molecule and one more here I am writing, see. What is its mirror image, you tell me? Tell me. COOH.
Right side H.
OH.
H.
OH. H. OH and CH2OH. Then these compounds are mirror images which are not superimposing, so we can say them as enantiomers. Now see what I am doing. How many chiral centers are there here? 1, 2, 3 chiral centers are there. So product same mirror image also have 3 chiral centers. Now what I am doing is I am just changing this one of these chiral centers configuration, like OH, H, OH. Now tell me whether these 1 and 2 are mirror images or not. No, they are not mirror images. Why? Because the configuration here is not changed at second chiral center right now. So it means these are not mirror images right now. So both of them are stereoisomers only now. What is the definition of stereoisomers? Isomers which are differ in the spatial arrangement of atoms. Yes, they are differ in the spatial arrangement of atoms because this is right side, here it is left side. Remaining everything is same. Okay, so it means what I can say, they differ in the spatial arrangement of atoms, so stereoisomers. But these are not mirror images, are considered as diastereomers. What I am giving a new word here? Diastereomers. So how can you define diastereomers?
The stereoisomers which are not mirror images and are not superimposable.
See, if they are not mirror images, they won't superimpose, that is fixed. Okay, no point of discussing again superimposability when it is not mirror image. Okay. Okay, so diastereomers is clear now. Okay, so now see, one factor you can write, when we have seen enantiomers, configuration of its mirror image, what happening if it is OH right side, here it is becoming left side. It is becoming left side. It means if it is R configuration, its mirror will be having S configuration when it is enantiomers. So to go from one enantiomer to another configuration must change at all chiral centers. It means all chiral center means, for example, our starting real image is having RR configuration. Then its enantiomer should contain SS. Its enantiomer should contain SS. If it is SS, RR. If it is RS, SR. Like that. Okay, and for diastereomers, configuration changes may changes at least one chiral center. I am not saying not all, at least one chiral center, not all. Okay, for understanding purpose you can observe this structure, this isomers. What happened? Configuration is changed at 2 chiral centers. If it is changed at all 3 chiral centers, we can say it as, if all 3 chiral center configuration is changed, enantiomer. If only 1 chiral center is changed, diastereomer. If 2 chiral centers changed, if 3 is changed, enantiomer. Only 1 change, if no change, no change means identical. What is that? Identical. Okay, so I will be making it more clear using this. I have starting material RR becoming SS.
Sir, R is clockwise and S is anti-clockwise.
No, it is not fixed like that. If R is clockwise, S should be anti-clockwise. If R is anti-clockwise, S should be that, like that. Okay, and I will tell you. That is experimental observation only. Okay. See, initially I have RR. It is becoming SS. It means what is this process? enantiomers. These are enantiomers. And SS becoming SR. What is this process? See, only one chiral center's configuration is changing, this is remaining same. So this is diastereomers. Next, what about this relation? RS becoming SR. R becoming S becoming R. So this is enantiomer. And what about this process? RR same, but R becoming S. Only one chiral center is changed. So it is diastereomer. Now what about this relation? RR becoming SR. So diastereomer. What about this relation? Diastereomer. Is this clear? Yeah. You can solve any questions related to this. Now once again, we'll tell you now one more thing. For understanding purpose, let us understand this RS nomenclature. RS okay, so there are other terms also, racemic mixture, meso compounds, all these things. To understand that, we'll make clarity about this RS nomenclature first. So it is an absolute configuration. What is this absolute configuration means? Configuration. By using some standard set of rules proposed by Kohn-Ingold Prelog. So I am calling it as CIP rules. Okay, by using some standard set of rules, we are assigning configuration at each chiral center. For example, I am writing Fisher projection like this: CH3, H, OH, and some CH2H5. Like this I am writing. Okay, tell me whether this carbon is chiral or not. Yes. Now, as per CIP rules, one basic rule I will tell you first. More atomic number, greater atomic number, more prioritized, more priority. Okay, now tell me which is greater atomic number here? Oxygen, carbon, hydrogen, carbon, oxygen. So first priority. Next, here also carbon, here also carbon. If it is carbon, go to the next one. Hydrogens only here. Hydrogens are there, but here carbon and carbon is in C2H5. So this is second priority. If same atomic number, next check for its molecular weight. In case of isotopes, I can say. Okay, then this is 2, and this will be 3, and this will be 4. Like this. Okay, now go from 1 to 2. How the rotation is looking like 2 to 3. Ignore 4. How it is? Clockwise right now. So this way of representation is called Fisher projection. So in Fisher projection, if it is clockwise, look at here carefully, clockwise with least priority group on vertical line. What I am saying? Least priority group on vertical line. What I am saying? If it is clockwise with least priority group on vertical line, then you should say it as R configuration. Okay? And if it is anti-clockwise, S configuration. Okay? When this scenario will be observed, least priority group must be on vertical line. But in the given example, the least priority group is on horizontal line. So if least priority group is on horizontal line, configuration becomes opposite. It means by practicing 2 more questions it will be easy. Wait. If clockwise, you should call it as S. If it is anti-clockwise, you should call it as R. When it is if our least priority group is on horizontal. So tell me, our least priority group is on horizontal or vertical? Horizontal. How is the rotation? Clockwise. So it is called as S isomer, S configuration. So this will be considered as no? S configuration. Is this clear or not? For practicing purpose, we'll look back into our previous questions here. Can you try to arrange, or can you try to assign the RS nomenclature here for this molecule?
Sir, but two are there, no?
No issues. Out of these two, just start here. This is a chiral center. Give for each chiral center, give separately. So this will be 1. To the carbon directly attached oxygen is highest atomic number 1. After that
2
CH3 here, but this side carbon is there now, connection to this carbon and carbon. After that hydrogens only, but here oxygen is there. So second group is here priority, and third one. So how this rotation? Clockwise. But least priority group is on horizontal line now, so it will become S configuration. Now what about the second chiral center? Tell me. This third carbon.
Which is
1. Next above group will be 2. Methyl group will be 3.
Anti-clockwise or configuration.
How is this rotation? Clockwise only now.
clockwise, and least group is in horizontal, so
Huh.
it's configuration.
Clockwise with the least priority group is in.
Horizontal. H is least, right, sir?
Yeah. So it will be
Yes.
S.
But which is optically
Once again, OH1, this is 2, so we are having clockwise direction. Clockwise means with least priority horizontal. So clockwise least priority group on horizontal means what we can say?
Sir, it is plane inactive only because plane is passing through it.
Yes, anyways, what we can give now, chiral center is present means we can give RS nomenclature. Okay, so yeah, so 1, 2, clockwise. So clockwise means
S.
it should be R, but least priority is on horizontal line, becomes S. Here also 1, 2, how is this rotation? Clockwise. With the least priority group is on horizontal, clockwise means R, least priority on here, so it becomes S. Okay, next we'll solve few more examples. COOH, COOH, HOH, HOH. This is called tartaric acid. What is it?
Tartaric acid.
OH, H, OH, H. Now tell me here, which is more prioritized? OH first, 1, and next between these two carbon and carbon, to that carbon oxygen is attached, okay, and to this carbon also oxygen is attached, but 2 oxygens but 2 carbons. So which is more prioritized? This one, 2. After this 3. This is 4. Now tell me where to go. I should go 1, 2. So this is anti-clockwise, but least priority group. So it becomes R. And here
Least highest is O.
1,
This is 2.
2, 3. So how it is? Anti-clockwise. Anti-clockwise with least priority group. Anti-clockwise means S generally, but least priority here means it becomes R. Both are RR only. And here you can come 1, 2,
3 down.
3. So
Anti-clockwise.
anti-clockwise, so it becomes R. What about here? 1, 2, 3. So clockwise, but least priority is on horizontal. So it becomes S. So now what I am saying here is, look at this molecule. If I pass a plane like this, what happens? Molecule will divide into 2 equal halves now. So we can say it is a meso compound. Meso compounds have plane of symmetry now. If I pass a plane like this, will it have plane of symmetry? No. OH, OH are at different side. But here, so plane of symmetry is present here. So plane of symmetry is present means meso compound, optically inactive. So now look at here, this is R direction, this is S. So R, S, what happens to the net rotation? Net rotation becomes 0, that's why this is optically inactive. But here it is, both are R only now, same direction both, so it will be optically active. So meso compound, meso tartaric acid is optically inactive, normal tartaric here it will be active. This is about absolute configuration. Now there one more term is there, relative configuration. What is this relative configuration means? See, CHO, OH, H, CH2, OH. This is glyceraldehyde. What is it? So now on these we have one chiral center now. At this chiral center, if OH is present right side, we are saying it as D-glyceraldehyde. What is that? D-glyceraldehyde. Okay. So now with respect to or with relating to the D-glyceraldehyde or relating to the glyceraldehyde, other molecules configuration is also defined. Similar to D-glyceraldehyde, if here OH is right side now, D configuration. And here OH is left now, you should use L, capital L, L configuration. So DL nomenclature is basing on what? Relative to?
Most prioritized group.
No, relative to what?
Oxygen.
Glyceraldehyde. So taking glyceraldehyde as a standard unit, other units, other compounds were compared with this. If it is having OH right side, we are calling it as D-glycerol now, D-glyceraldehyde now. Here also it is right side, so it should be here L.
What if no H in the...
If not OH, if we have NH2, simple way I can tell you, more electronegative group you can check. If it is right side, like if NH2 is right side, that is also D. If NH2 is left side, L. This will be seen in case of amino acids. Okay, so naturally occurring amino acids are there now. Those are having, mostly they are having L configuration. And when it comes to carbohydrates, like biomolecules we will be seeing now, glucose, all these things, they will be having D configuration, most of the compounds, which are naturally occurring. Okay. Okay, next. See, what do we mean by enantiomers? Once again, tell me.
Enantiomers not superimposable and 3 character configuration is changed.
Why you are getting that much? I mean, you are suffering a lot to answer this. So, stereoisomers which are not superimposable mirror images.
Character configuration is not same.
That is what? If they are not if they are not superimposing, it means their chiral center is not same only. Stereoisomers which are not superimposable, they are considered as enantiomers. Now let us take one example. This side is CH3 and here one hydrogen, one C2H5 group, one H and one OH. Tell me which group is more prioritized here? 1. After that 2, 3, 4.
Clockwise.
So clockwise. What is it?
Least prioritized group is
Always remember least priority group should be on dash line. Dash line. If clockwise, consider it as R. If anti-clockwise, consider it as S. And if least priority group is on solid line, if clockwise, S, anti-clockwise, R. That's it. Like opposite of this thing. Now tell me,
in plane.
In plane if it is present, you need to rotate it. Okay. Now tell me what about this?
It is on
clockwise rotation, least priority on dashed line. It means R. Okay, and I am taking one more example here. CH3, C2H5, OH, H. Tell me here.
Anti-clockwise.
So 1, 2, 3. How it is? Clockwise. Clockwise rotation is there, but least priority is on.
Solid line.
It becomes
Opposite.
opposite. It means it is S. So I have R configuration, S configuration. This is nothing but, just look at here, I am taking a mirror here. Consider we are taking a mirror here. Tell me, these are mirror images or not? Ethyl group like that. So OH becomes, see, above the plane becomes below the plane in mirror, below the plane become above the plane if I place a mirror here. Okay. So now, if I take equimolar mixture of R and S isomers, I am taking a jar. Previously what I have? Pure R I have, pure S I have. I am taking equimolar mixtures like 50% S, 50% R into a jar. Now what happens? That mixture contains 50% of S and 50% R. So now tell me, what if I pass the plane polarizer light through this? What happens?
Undeflected or some.
It won't have any deflection. Why? There is no rotation of plane polarized light. Why? Because equimolar mixture of R and S configuration compounds are there. Okay, I am saying racemic mixture. It means mixture of two isomers, stereoisomers, enantiomers. So you can write a term, new term here, racemic mixture. Mixture. What is this racemic mixture means? Sorry. Equimolar mixture of two enantiomers. Two enantiomers is called racemic mixture. So in the short form it is written as RM or 1 plus 1 minus. Why 1 plus and 1 minus? Just now I told you, equimolar mixture of two enantiomer. One enantiomer if it is plus direction, another one will be minus. Having equimolar mixture na, equal amounts na, that's why it is represented like this. Now when I explained you about meso compounds, I told you that they are optically inactive due to internal compensation. Within the molecule there will be one S direction, one R direction. But here two separate molecules, na, two separate isomers, na, stereoisomers, na, we are mixing them. It means racemic mixture is optically inactive due to external compensation. What is this internal external? What's here?
One is internal within that.
Within the molecule if present? Internal. That is seen in case of meso. And this is
Racemic.
External compensation. It means two enantiomers we have. Okay. So equimolar mixture of two enantiomers is called racemic mixture. For example, I am taking 2 ml R configuration plus 2 ml S configuration. Now what happens? Equimolar mixture, na, resultant solution will be optically
Plus or minus.
inactive. Okay, so optically inactive. What is the reason? Due to external compensation you can write. Now if I want to separate these two isomers from this racemic mixture, the term we can define here is resolution. What is that? Resolution. So what is mean by resolution? The process of separation of enantiomers from its racemic mixture. What is resolution once again? The process of separation of enantiomers from its racemic mixture. Okay. So these are the terms you need to know, right? So in the next class we'll start GOC. from the very beginning. Okay, so now you just open your target modules if you have and try to solve some questions related to optical activity and isomerism. Okay.